We have constructed our cover. Recall that we have X connected, locally path connected, semi-locally, simply connected, and let's say G equals pi 1 of X, X0, and H is a subgroup of G. Okay, so we constructed Y as omega hat, that is paths beginning at X with X0, ending of X, by equivalence relation, where alpha is equivalent to beta if and only if alpha 1 is beta 1, and which alpha star beta bar, the class of this is in H. Okay, so this is a loop at X0. Now, we also have a map P from Y to X, which is the obvious map, which is going to be P of alpha is going to be alpha of 1. And what we want to show is this is actually a cover, and now we need our hypothesis that it's locally path connected and semi-locally simply connected. And recall also that we have a topology on this space. So on Y, so we have basic open sets. They were called U gamma. They depend on a set U as well as open set U in X and a set gamma. It's the class of all paths gamma star eta. Okay, where so gamma is a path that goes to an endpoint. So where let's say eta maps 0, 1 to U. And if gamma is fixed, I can say eta of 0 is gamma of 1. So this product is defined. So I have a X0. I have a point X here, and I have a fixed path, and open sets are paths here. Okay, we remarked last time that things are quite bad if it's not locally path connected. In that case, if I took J equals H, then I have an identity map. So as sets, this is if your G equals H, you see this condition alpha star beta bar is in H is automatic. So it's simply paths up to endpoint. And when you're talking about paths identified, if their endpoints are identified, that means as a set you're just looking at their endpoints. You're ignoring everything else. But the topology is the same as the topology on the space X, only provided you're locally path connected. Okay, and we'll show something, of course, more general than this. What we want to show is so the theorem, first of all, is that Y is a P from Y to X is a covering map, and then we'll have a second one which will tell us what the fundamental group is, but that will more precisely the image of the fundamental group. Okay, but that will come to next. Right now we'll concentrate on showing it's a covering map. So let's look for an evenly covered neighborhood. And well, what is an evenly covered neighborhood? Well, we can look at simply connected neighborhoods or semi-simply connected neighborhoods, which we have in our context here. Okay, so semi-simply connected means so let's pick a point X. Let X belong to X. Okay, and let U contained in X be open such that U is path connected and pi 1 of U X to pi 1 of XX is trivial. So here's a question: why does this exist? It may seem obvious. It's locally path connected and semi-locally simply connected. Okay, so let's pretend even locally simply connected. But that's not good enough, because it often happens that you have two properties which are true locally. That means given a point and given a neighborhood of that, there's a smaller neighborhood which has property 1 and a smaller neighborhood of this which has property 2 but may fail to have property 1, and yet another smaller neighborhood has property 1 again, and so on. And this is not infrequent in real mathematical situations. When you want to have two properties and they are whole locally or asymptotically or something like that, asymptotically is fine because that's a stable thing, and indeed for much the same reason, you see, because this point is hereditary. If I have a set with this property being trivial, any smaller U also has this property. That's why when I take a U which has this and I take a smaller set, open set which has the Okay, and of course I also want x and u, and take an even smaller open set which is path connected, it will continue to have this property. Okay, so that is the point that we have. We can ensure both these properties. Okay, so what we want to claim is that uy, so consider, okay, so we'll consider, so we are connected, so let gamma be a fixed path from x0 to x. We don't need this actually right now, so let's not pick this thing here. We'll keep it here, but we are going to ignore this. So what we'll claim here is that U, which was this sort of semi-simply connected neighborhood, is evenly covered. Okay, so evenly covered. So what are the chaps here? By what? Okay, so well, let's look at the fiber over x. Okay, so the fiber over x is, by definition, we are looking at equivalence classes of curves. So fiber over x is going to be equal to equivalence classes of curves from x0 to x divided by the appropriate equivalence. Okay, and the appropriate equivalence is, as usual, alpha star beta bar belongs to H, which is, in H is trivial, it's nothing, and when just having the same endpoints, so when the endpoints are fixed as x, it's nothing. At the other extreme, it's being homotopic. Okay, so fiber over x is this, and let's pick representatives for the fiber. Gamma I, let's say I is in some index set. It need not be countable or anything like that. So we have an index set. We are picking representatives gamma I in this thing. Okay, so that is that we have the fiber is exactly the set of gamma I, and all of these are distinct from each other. Okay, this is the representative that we have, and now we can give neighborhoods. Okay, so let Vi be the neighborhood U gamma I. Okay, and this is for all of the index set I in I. Okay. So this gives you a bunch of open sets. So we have the point x here, we have the point x0 here, we have U, okay, and we have a path, some particular gamma I. Okay, and elements in Vi are classes of this followed by eta, where eta is contained in U. Okay, so the endpoint is going to lie in U. Okay, so then by construction, what we have, so P maps Vi to U itself. Okay, so far we don't know that it's onto, we don't know that it decomposes and so on. So what are the things we have to show? Our first lemma here is that these are disjoint from each other. Okay, so that is, but let's first, before we prove that disjoint from each, let's first prove that P restricted to Vi surjects onto U. P restricted to Vi, mapping Vi to U, is onto. Well, what do I have to do? Suppose I have another point x prime here. Okay, so let's make some space for it by getting rid of these. Okay, and let's add some color. So here I have a point x prime, and I'll take a path from here to here, okay, which joins these two. Then what we have is that we can connect x to x prime, because this is path connected. That's what we did when choosing that path. Let's call that path eta, that goes from x to x prime. Okay, so once we have this, it's easy to see that we have an element in Vi. So we have, so given proof is, so suppose we are given x prime in U, let eta be a path in U from x to x prime. Okay, So then what we have is the class of gamma I star eta. This class is by definition contained in U gamma I, and of course P of gamma I star eta is going to be equal to the point we want x prime. Okay, so each of them separately surjects, and the most subtle point is their disjoint. So this is just path connectedness. Okay, so that is Vi if I is not equal to j, both in the index set I, then Vi intersection Vj is the empty set. Okay, so this is what will take a little more time to prove. Okay, so let's enrich our picture a bit. Okay, so the point is that if I have an element in Vi, any element in the Vi is of the form the class of gamma I star, let's say eta I. Okay, and similarly here. So suppose we have an element here an element in the intersection, then gamma I star eta I is going to be equal to gamma j star eta j. Okay, where gamma I and eta I is j. Okay, so hence in particular the endpoints will be the same, and if I look at gamma I star eta j bar, and I'm going to put these, group these together, star gamma j. What do we know about this? Well, this guy has to belong to H. But now we have something nice. Okay, so this is contained in U, and as a result this is homotopic to the identity. Okay, so this implies that gamma I star gamma j bar, I'm sorry there was a bar missing here, is in H. Okay, that is that gamma I is equivalent to gamma j. Okay, but that implies I equals j because we took coset representatives. So while I stated this as contradiction, no, you could take it as a direct argument. If Vi intersection Vj is non-empty, so the picture here is worth seeing. I had gamma I and I have another curve gamma j, which is something different. It represents a different coset. Okay, and then I had an eta I and then a little orange curve which was eta j, let's say. And what I know is that they have to end at the same point if they have if they're in the intersection. But what I know is that if I make a loop, which is one of these followed by the little one and a little one, and then back again, what I end up with is an element in H. But the thing is, because of our semi-simple connectivity hypothesis and choice of U according to that, this little loop is homotopically trivial. Not necessarily in U, but homotopically trivial in X. As a result of that, we get the claim that these are disjoint from each other. Okay, so we are almost done now. What we have seen is that we have a bunch of onto maps, and these are disjoint neighborhoods. They are open by construction. Okay, what all I'll do now is we'll construct a section, and very similar arguments can show that this is continuous. So we have our local inverse map, which we'll see have, oh, sorry about that, local inverse, which is going to have to be a map from U to Vi. Okay, and that is kind of obvious. It's just like our map lifting. We have x0, we have x here. Okay, and remember, for a fixed I we have a fixed path gamma I here. Okay, and now if I take a point x prime, I pick a path eta joining these two. Okay, and so let's and then we take the class of this wedge eta. So P of x prime is the class of gamma I star eta, and the point here is that this is independent of eta. First of all, eta exists because of local path connectivity. But if I took a different curve which is orange, there is a loop. Again, that loop may not be homotopically trivial here as it looks, but it's homotopically trivial in the whole space. As a result, this guy is going to be independent of eta. So as you see, again, we use the hypothesis that things are not semi-locally simply connected. It's actually a nice exercise to take a space like the Hawaiian earrings, which violates one of our hypotheses. And the construction makes complete sense. But see how the steps about it being a covering fail. Okay, so you'll see a point sort of splitting out into two depending on which direction you approach it. And indeed, if you allow yourself to cross the origin, split out into infinitely many copies, which is at some level desired. It's what you do with S1, you make infinite fibers, but even locally it's happening. Okay, so that violates it. So we are almost done. Now we'll have to do two things. We have to prove that we have the correct cover. We just constructed a cover using H, but we don't know that this is the cover for H. That is a nice little relaxing argument. And finally, we summarize our theorem, which is the fundamental theorem of Galois theory for covering spaces. Okay, so with that, we'll be done with this portion.